Modern artificial intelligence systems process language as a landscape of computable statistics. To make text machine-readable, engineers strip away linguistic nuance, discarding irony, subtext, and cultural weight, forcing raw strings into rigid mathematical geometries. This computational translation relies on human-supplied labels to establish its ground truth, anchoring every node in geometric space to a subjective human decision. Tracing the complete life cycle of a natural language processing model reveals how text moves from a raw string to an embedded matrix, through human supervision, and finally into a state of systemic failure. Algorithmic bias and privacy leaks emerge from the specific structural choices made throughout this translation pipeline. This NLP pipeline operates through an architecture of 4 distinct transformations. Layer 1, discretization, breaks down raw text. Layer 2, representation, maps those pieces into a mathematical space. Layer 3, supervision, applies human rules, and Layer 4, vulnerability, represents the final systemic output. Auditing this pipeline provides an empirical method to see how vulnerabilities are engineered at scale. Raw text strings are useless to a neural network until they are mechanically discretized into atomic units called tokens. Byte pair encoding is the primary method for this subword tokenization. The algorithm evaluates character frequencies to split language into measurable chunks. It begins with individual characters and iteratively merges the most common adjacent pairs. Common character sequences eventually fuse into the final discrete tokens. This process establishes the absolute vocabulary limit for the entire model. Data uncertainty, or polysemy, occurring at this foundational atomic level, permanently restricts the model's downstream capabilities, as the system cannot reconstruct nuance lost during discretization. Because discrete tokens cannot convey relationships, the system requires a continuous semantic representation to perform computations. In a continuous bag of words, or CBOW architecture, the process starts with a one-hot encoding of context tokens. Multiplying this input against a dictionary matrix V condenses the data into a dense context vector within a hidden layer. A second multiplication against matrix V prime generates prediction scores, followed by a softmax application that converts those scores into a probability distribution over the dictionary. The skipgram architecture inverts this objective, using a single target word to predict the surrounding window of context words. This inversion creates a performance trade-off, where CBOW offers faster computation, while skipgram achieves higher accuracy for infrequent words. Semantic relationships in this vector space are expressed as literal geometric distances. Subtracting the vector for man from brother and adding woman places the resulting coordinate closest to the vector for sister. By reducing semantics to geometric distance, Word2Vec establishes the mathematical framework that allows human bias to be encoded into the model. Geometrically plotted vectors lack task-specific utility until human ground truth is applied. Engineers use named entity recognition to classify text into defined categories. Human annotators manually classify individuals using a person tag. They define companies and groups with an organization tag. Physical landmarks and geographical coordinates receive a location tag, and brands or manufactured items are assigned a product tag. The BIOES scheme identifies the boundaries of these entities by marking the beginning, inside, and ending of phrases, identifying single-word entities, and flagging everything else as outside. Manually labeling millions of text strings at scale creates a severe operational bottleneck. To bypass this, engineers use active learning to select only the most informative examples for human annotation. This process balances 2 strategies: exploitation, which uses uncertainty sampling to find the data points the model is least confident about, and exploration, which samples diverse clusters from across the entire data distribution. A model's accuracy is ultimately bound by the human annotator's strict taxonomy and the statistical skew inherent in the active learning strategy. Imbalanced source data causes the Word2Vec dictionary matrix to encode those imbalances geometrically. Social bias alters the spatial distance between tokens, causing professional terms to warp towards specific gender vectors based on real-world stereotypes. Predictability vulnerabilities emerge from data uncertainty, such as lexical irregularities and polysemy that were not resolved in the initial layers. Model uncertainty, including overfitting and poor generalization, leads to outputs that are highly confident yet inaccurate. Privacy vulnerabilities exist because tokens can map back to specific user inputs, allowing models to leak personally identifiable information. Differential privacy mitigates this by injecting statistical noise into vector mappings to obscure individual contributions. Locality-sensitive hashing further protects data by transforming raw text into binary codes during the processing stage. Bias, unpredictability, and privacy breaches are the mathematically computed consequences of decisions made during tokenization, embedding, and labeling. The completed 4-layer NLP pipeline illustrates the technical reality of modern language systems. Technological capabilities in deep learning have accelerated on a steep exponential curve over the last several years. Development of ethical mitigation strategies has lagged significantly behind these technical gains. The delta between technical implementation and ethical standard setting is the responsibility gap. Allowing technical capabilities to vastly outpace ethical standards fundamentally endangers the reliability of artificial intelligence. Ethical failures in natural language processing are structural features of how we compute meaning. Data scientists must treat ethical evaluation with the same mathematical rigor applied to optimizing a loss function. Therefore, quantifying uncertainty and actively applying differential privacy are now considered mandatory engineering requirements for stabilizing the neural network. Rigorous engineering requires auditing the pipeline from the first token to the final label. The scalability of NLP depends on mastering the unpredictable, human-in-the-loop realities of the pipeline.